Here I will explain second order low pass Butterworth filter analysis. Op amp is in non-inverting configuration. Op amp is in non-inverting amp configuration. Therefore, in case of non-inverting op amp configuration, AF is equal to 1 plus RF by R1. Gain AF is equal to 1 plus RF by R1. In this frequency response, in case of first order filter, the gain rolls off at a rate of 20 dB per decade. First order. In case of first order low pass filter, low pass Butterworth filter, the gain rolls off at a rate of the gain rolls off at a rate of 20 dB per decade. This one is second order Butterworth filter. The gain is the rolls of my 40 dB per decade. 40 dB per decade. The slope of the frequency response. This is the slope. The slope of the frequency response after f is equal to fh is minus 40 dB per decade for second order low pass filter. Two bands are there, pass band and stop band. Pass band allows frequencies, stop band attenuate the frequencies. At f is equal to fh, the gain is decreased, voltage gain is decreased by a factor is equal to AF by root 2 or 0.70 times AF. Whenever F is less than FH, the gain, pass band gain is constant. Here F less than FH, that is cutoff frequency. The gain is constant. The pass band gain is constant. The pass band gain is constant. That is equal to AF. Gain, voltage gain. Voltage gain. A, it is be represented by A is equal to AF. Yet F is equal to FH, voltage gain A is equal to AF by root 2 or 0.707 times AF. At F greater than FH, the gain, the frequency response after FH is the slope of the frequency response after F is equal to FH is minus 40 dB per decade for second order filter. This is the frequency response of that second order filter. Now analysis of second order low pass Butterworth filter. Here one more important point here. The first order filter can be converted to second order type by using an additional RC circuit. R3 and C3 an additional RC circuit is attached to first order filter. The cutoff frequency fH for this filter is now decided by R2, C2, R3, C3. This is the description of the second order low pass filter. The op amp configuration here is inverting, non-inverting configuration. The gain of that non-inverting op amp configuration is AF is equal to 1 plus RF by R1. Here coming to frequency response. At F less than FH, the pass band gain is constant, that is equal to AF. At F equal to FH, the voltage gain, AB is equal to the voltage gain A is equal to AF by root or 0.707 times AF. Yet F greater than FH. The gain is voltage gain. A is rolls of at a rate of 40 dB per decade. Slope is minus 40 dB per decade. Next one coming to analysis. Some more important point here is the first order filter, or here Butterworth low pass filter. First order Butterworth low pass filter can be converted to converted to second order type by using an additional RC network. This one, the additional RC network means R3 C3. That the cutoff frequency FH for this filter is now decided by R2 C2 R3 C3. Second point is the cutoff frequency FH for this filter is now decided by R2 C2 R3 and C3. One more important point is gain of that opamp is in non-inverting configuration of that second order Butterworth filter is 1 plus RF by R1. The gain of the filter is usually decided by opamp, that is resistors R1 and of RF. The gain of the filter is as usual decided by opamp. That is the resistances R1 and RF. These are some important point related to second order Butterworth low pass filter. Now I will concentrate on analysis of filter circuit. Determine the cutoff frequency of this filter circuit. Consider this portion V in R2 C2 R3 C3. Find out by using this network. Find out A. One end of C2 is connected to here. Another end of C2 is connected to V0. Analysis of the second order Butterworth low pass filter. Take this portion. This one is plus minus V in R2 1 by, here we use C2. One end of C2 is connected to here. R3. This one is R3. Another capacitor is here is C3. Here the voltage is VA. This one is connected to half amp, inverting terminal of that half amp. Here C2 another end is connected to V0. Here V in, here ground, here ground, like that. Here at this point, a node is created that the node voltage is equal to V1. Here we use the capacitive reactance is equal to, we know that 1 by j omega C2. Convert this into Laplace transform. S is equal to j omega. Capacitive reactance XC2. 1 by j omega C, that is equal to 1 by S is equal to j omega 1 by S2. SC2. XC3 is equal to 1 by j omega C3, that is equal to S is equal to j omega S C3. Convert this into 1 by SC2 and 1 by S C3. 1 by S C2 and 1 by S C3. Now apply nodal analysis at point V1. Nodal analysis at point V1 and VA, and calculate gain, the frequency gain, output voltage by input voltage, V0 by Vin, and then calculate transfer function. Compare this transfer function with the original transfer function. Find out the cutoff frequency of the second order Butterworth low pass filter. Here calculate the apply nodal analysis at point. Apply nodal analysis at V1. At V1 apply nodal analysis. Apply nodal analysis at point V1. That node voltage V1 into some, what are the branches are connected to that node V1? R2, R3 and 1 by SC2. Consider admittances of these branches. Admittances of these branches. Admittance of R2 is 1 by R2. Admittance of R3 is 1 by R3. Admittance of capacitance is equal to SC2. SC2. And adjacent node voltages VA and Vin, and V0 is also there. V0 is also there. Minus adjacent node voltage, that is V0, into admittance of that capacitance C2 is SC2, minus adjacent node voltage is V1 is Vin also. Vin minus Vin, admittance of R2 is 1 by R2. Here another adjacent node voltage is there, VA. VA minus VA into 1 by R3. Minus VA into 1 by R3 is equal to 0. Is equal to 0. This is the equation 1. Further simplify this equation 1. We use LCM. LCM here. R2, R3. V1 into, here R2 is there. That is R3. Here R3 is there. R2. Both here 1 is there. 1 means multiply SC2 with R2 C3. SC2 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 R2 R3 close. Here minus V0 SC2 or minus V0 S C2, R2, R3. Here minus V in. Here R2 is there, minus V in R3, minus V naught. R3 is there. R3 is there. Here V naught is multiplied with R2 is equal to 0. That is equal to V1 into R3 plus R2 plus S C2 R2 R3 minus V naught S C2 R2 R3 minus V in R3 minus V naught R2 is equal to 0. R2 is equal to 0. This is the equation 1. Simplified equation 1. Now apply nodal analysis at VA. At VA. Here VA into at VA into what are the admittance are connected to this one, this VA node? 1 by R3 S C3 minus adjacent node voltage is minus V1 by R3 is equal to 0. This is the nodal equation at this node. This node already at V1 the analysis is completed. Simplified this one. This is equal to VA into 1 plus S C3 R3 by R3 is equal to V1 by R3. Therefore, finally, V1 is equal to VA into 1 plus SC3 R3. This one V1 is equal to VA into 1 plus SC3 R3. This is the equation 2. This is the equation 1. This is the equation obtained. Apply nodal analysis at VA point. Substitute V1 in that expression. VA replace V1 here. VA into 1 plus S C3 R3 R3 plus R2 plus SC2 R2 R3 minus one more important equation here is here one more minus adjacent voltage is minus VA by here minus here VA here also VA. Simple modification because the adjacent voltages of V1 are V in, V naught, VA. Instead of VA, I used it a V naught. Therefore, here VA. Here I put wrong V naught. Instead of V naught, we use VA. Here VA. 1 plus SC3 R3 minus R2 VA is equal to bring this entire term in this side. V naught S C2 R2 R3 plus R3 into V. R3 into V in. Again, total VA is equal to here VA 1 plus S C3 R3 R3 R2 plus SC2 R2 R3 minus R2 is equal to V naught SC2 R2 R3 plus V in R3. V in R3. Therefore, finally, VA is equal to R3 into V in plus V0 SC2 R2 R3 by 1 plus SC3 R3 R3 plus R2 plus SC2 R2 R3 minus R2 minus R2. This is the VA. The node voltage at is the voltage at VA. This is the voltage at VA. According to virtual ground concept, the voltage at A is same as the voltage at B. VA is equal to VB. Here, apply nodal analysis at the point B. That means VB into what are the admittance are connected to this point 1 by R1 plus 1 by RF. This is the ground minus 0 by R1. This is the V0 minus V0 by RF is equal to 0. Therefore, VB into RF plus R1 by R1 RF is equal to V0 by RF. RF cancel. Therefore, VB into 1 plus RF by R1 is equal to V0 is equal to V0. Therefore, finally V0 is equal to VB. VB is equal to VA. VB is equal to VA. V0 is equal to VA into 1 plus RF by R1. 1 plus RF by R1 is AF. 1 plus RF by R1 is AF. Therefore, V0 is equal to VB. VB is equal to VA. VA into 1 plus RF by R1. 1 plus RF by R1 is AF. Here we use the non-inverting amplifier configuration. Therefore, VA into AF. Substitute VA in that expression. Therefore, V0 is equal to VA is entire expression. VA is R3 into AF. R3 V in AF plus V0 SC2 R2 R3 AF by 1 plus SC3 R3 plus R2 plus SC2 R2 R3 minus R2 minus R2. Bring this entire term here. Here R2 is there. Here R3 is there. R3 is common term. Further simplified this one. V0 minus V0 AF V0 AF S C2 R2 R3 by this entire term. This entire term, let it be some y. Let it be some y is equal to R3 V in AF by y. Therefore, here V naught y minus V naught AF SC2 R2 R3 by y is equal to R3 V in AF by y. Y cancel. Therefore, V naught is the common term. Therefore, V naught into y minus AF SC2 R2 R3 is equal to R3 V in AF. R3 V in AF. Therefore, finally, V naught by V in is equal to R3 AF by y minus AF SC2 R2 R3. Now substitute y here. Y here. Y is equal to, we know that y is equal to 1 plus S R3 C3 R2 plus R3 S R2 R3 C2 minus R2. Simplify this. 1 is multiplied with an entire term, that is R2 plus R3 plus S R2 R3 C2. This SR3 C3 is multiplied with an entire term S into R2 R2 R3 C3 plus S R3 square R3 S R3 square C3 next one S square R2 R3 square C2 C3 minus R2. Here R2 is cancelled. R2 is cancelled. The R3 term is common here. 1 plus S R2 C2 plus S R2 C3 S R3 one S3 one R3 is common R3 C3 S square R2 R3 C2 C3. This is the y term. Substitute this y term in the equation here. Therefore, output voltage gain A is equal to V naught by V in is equal to R3 AF. Here R3 y is equal to R3 1 plus S R2 C2 S R2 C3 S R3 C3 plus S square R2 R3 C2 C3 minus this term AF S C2 R2 R3 minus AF minus AF S. R3 is common. R3 is common. S C2 R2. S C2 SC2 R2. Here actually minus AF S C2 R2 R3, but R3 is common term. Therefore R2 is cancelled. Therefore gain A is equal to AF by S square R1, not R1, R2 R3 C2 C3 plus S into R2 C2 plus R2 C3 R3 C3 minus AF R2 C2 plus 1 plus 1. That is equal to gain A is equal to AF by S square R2 R3 C2 C3 plus S into R2 C3 R3 C3 plus R2 C2 into 1 minus AF 1 minus AF plus 1 1 minus AF plus 1. Therefore gain A is equal to entire equation A is equal to AF by AF A is equal to AF by common term is here is common term R2 R3 C2 C3 is the common term R2 R3 C2 C3 S square plus S into R2 R3 R2 C3 not R3 R2 C3 plus R3 C3 R2 C2 1 minus AF by up to this one by R2 R3 C2 C3 plus 1 by R2 R3 C2 C3 1 by R2 R3 and C2 C3. This is the second order Butterworth filter. Therefore finally A is equal to some gain factor M omega H square M omega H square, that is S square plus omega H S by Q plus omega H square. This one is omega H square is equal to 1 by R2 R3 C2 C3. M is equal to A. M is equal to A. Therefore, here gain A is equal to AF by R2 R3 C2 C3 pi S square plus S into R2 C3 R3 C3 by R2 R3 C2 C3 plus 1 by R2 R3 C2 C3. Compare this one. Omega H by Q is equal to this term. M is equal to AF. Omega H square is equal to 1 by R2 R3 C2 C3. Omega H square is equal to 1 by R2 R3 C2 C3 and omega H by Q. Omega H by Q is equal to R2 C3 plus R3 C3 R2 C2 1 minus AF by R2 R3 C2 C3. Again omega H square is like that. 1 by Q is the passband parameter. 1 by Q is L. 1 by Q is L. Okay. Therefore, omega H is equal to 1 by square root of R2 R3 C2 C3. Omega H is equal to 2 pi FH 1 by square root of R2 R3 C2 C3. Therefore, FH is equal to 1 by 2 pi square root of R2 R3 C2 C3 C2 C3. This is the A is equal to M omega H square by S square plus omega H S by Q plus omega H square. If R2 is equal to R3 is equal to R, C2 is equal to C3 is equal to C, I have to obtain some values. And here R2 is equal to R3 is equal to R, C2 is equal to C3 is equal to C. Therefore, cutoff frequency of that second order Butterworth low pass filter is 1 by 2 pi R into R C into C. That is equal to 1 by 2 pi square root of R square C square. That is equal to 1 by 2 pi RC. Cutoff frequency of the Butterworth low pass filter. And find out the gain here. A is equal to, we know that AF by R1 R2 not R2 R3 R2 R3 C2 C3 C2 C3 by S square plus S into S square plus S into that value is very important. S square plus S into S into here R2 C3 R2 C3 R2 C3 plus R2 R2 C3 R3 C3 plus R2 C2 into 1 minus AF by divided by R2, R3, C2, C3 plus 1 by R1, not R2, R3, C2, C3. Substitute these values. R2 is equal to R3 is equal to R. That is equal to AF by R square, C square by S square plus S into RC plus RC plus RC into 1 minus AF by R square, C square, R square, C square plus 1 by R square, C square. That is equal to AF by R square, C square, AF by R square, C square. Simplify this one by S square plus S into RC plus RC plus RC. 3RC minus RC AF by R square C square plus 1 by R square C square. AF by R square C square. S square plus S into RC is the common term. 3 minus AF by R square C square. R square C square by 1 by R square C square. Therefore, AF by R square C square S square plus S into 3 minus AF by RC plus 1 by R square into 1 by R square C square. This is the A. This is the A. When R1 is R2 is equal to R3 is equal to R, and also C2 is equal to C3 is equal to C2 is equal to C3 is equal to C. Second order Butterworth filter. The midterm required is root 2 is equal to midterm 3a minus 3a minus AF by RT. This is the midterm required is that is equal to root 2. 1 point RC is not required. This is the Butterworth second order low pass filter. 3a minus AF is equal to root 2. That is equal to 1.414. AF is equal to 3 minus 1.414. That is equal to 1.586. We know that AF is equal to 1 plus RF by R1. Therefore, RF by R1 is equal to 1.586. 1.586. Therefore, RF is equal to 1 minus 1.586. That is equal to 0.586 RF by R1. Therefore, RF is equal to 0.586 R1. This is the gain controlling parameters, resistances R1 and R2, RF and R1, and R2 is equal to R3 is equal to R, C2 is equal to C3 is equal to C, FH is equal to 1 by 2 pi R. These are the equations which are used in design the second order Butterworth low pass filter. Second order Butterworth low pass filter. Now coming to this one, consider general expression. A is equal to AF into omega H square by S square plus omega h s by q plus omega h square. AF, simplify this term, AF omega h square by omega h square is the common term, s square by omega h square, that is equal to omega suffix h s by q omega h square plus 1. Here omega h square and omega h square is cancelled. A, you put s is equal to j omega, a of j omega, that is equal to af by s is j omega whole square, that is omega h square, omega h, s is j omega, q omega h square plus 1. In case of af, that is equal to af by j omega by wh whole square, omega h and omega h is cancelled here, that is equal to j omega by q omega h plus 1, that is equal to af by omega is equal to 2 pi f, omega is equal to 2 pi fh, that is 2 pi fh whole square, 2 pi is cancelled, plus 1 by q is the alpha, j alpha. Let in case of Butterworth filter, 1 by q is the damping factor, that is equal to alpha. Passband ripple, that is alpha. Omega by omega is equal to 2 pi f, omega h is equal to 2 pi fh plus 1. 2 pi is cancelled, that is equal to af by 1 minus j square is minus 1, that is the minus f by fh, whole square, that is f square h square, that is f square and h square plus j into alpha f by fh, j into alpha f by fh. Find out the magnitude of that one. Mod a is equal to mod af is af by square root of 1 minus f square fh square whole square alpha f by fh whole square, that is equal to af by square root of a square, 1 square is 1 plus b square means f power 4 fh power 4 plus 2 minus 2ab, minus here minus 2ab, here minus 2ab minus 2 f square fh square plus here alpha square f square fh square. But in case of Butterworth filter, alpha is equal to root 2. Alpha is equal to defined value. Therefore, f is equal to, remember this value, 1 plus f power 4 fh power 4 minus 2 f square fh square. Root 2 means alpha square means 2 f square fh square. These two terms are cancelled. Therefore, finally AF is equal to magnitude A is equal to AF by A is equal to AF by square root of square root of square root of 1 plus f by fh whole power 4. Fh whole power 4. This is the magnitude magnitude term, magnitude of that magnitude of that gain for second order filter. For nth order filter, magnitude function is AF by square root of 1 plus f by fh whole power 2n. For n is equal to 1, first order Butterworth low pass filter n is equal to 1 AF by square root of 1 plus f by fh whole square. For 2, 2 into 2, 4. AF by square root of 1 plus f by fh whole power 4. This is the magnitude function. This is the magnitude function. This one is gain versus frequency. At f equal to 0, at f equal to 0, mod A is equal to AF. At f equal to fh, at f equal to fh, f by fh 1 power 4 is 1 plus 1 is 1 2 root 2. Therefore, mod A is equal to AF by root 2. Mod A is equal to AF by root 2. This is here. Mod A is equal to AF by root 2 here. At f equal to fh. At f equal to fh. Slope is here. Slope is minus 40 dB for decade. Minus 40 dB for decade. This is the pass band. Pass band. This one is stop band. This one is stop band. This is the entire analysis of that second order Butterworth low pass filter. Here f is less than fh. Here f is equal to fh. Here f greater than fh. This is the total analysis of the low pass second order Butterworth filter. With this, the analysis of that filter is completed.